Hello everyone, today we are talking about etching and let's start. Etching is to remove materials identified by the lithography, and this is we can talk this is removing selectively only the parts that are non-masked. And in etching target, there is silicon. There are silicons and silicon dioxide and silicon nitride and metals. And MEMS process is can you see this picture figure? This means making special structures like this, and we will talk about CESL. We call it sigil. And sigil is using an enchant that can etch as silicon oxide, as SiO2 or uh, silicon, but cannot etch silicon nitride. And this is like this use like a barrier. And we will talk about figure of merit of etching, and etch rate, uniformity, and etch profile, and etch selectivity. And first we'll talk about etch rate. Etch rate is how many we etched in same time, and if when the temperature goes down and the etch less uh, decrease and the temperatures increase, the etch rate is also increase. And this is a graph of etch time and etch depth. Etch depth is how many we etch in device. And uniformity is when the distribution of vapor is uniformed, and we can create the device shape that we wanted. And we'll talk about edge profile. There are two things in edge profile. First, anisotropy etching. This means etching in only one directions, and there is one thing on other thing on edge profile that is anisotropy, and it means etching in all directions. And can you see this formula? This AF means degree of isotropy, how this device is isotropy, and RAT and RVR. This RAT is this horizontal line, and this means speed of laterally etching, and RVR is means speed of etching vertically. And if AF, degree of isotropy, is near 0, we can call that it is isotropy etching. And AF is near the 1, we can call it anisotropy etching. And here, this is a figure of isotropy etching. This is, can you see this round shape? This is the edge. We etch that in all directions, so we can this round shape. And in isotropy that we in isotropy we can call the RIT and RVR is same, and this is masking layer, this is barrier, and this is silicon. This barrier is etching target, and this is we called DM, and this called we call DF. We will show this figure, and this is anisotropy etching. This is DM and this is DF. Can you see this? And DM and DF, we can see the DM and DF is same. And we will call bias B. This is DM, and how different of DM and DF, the difference of DM and DF. And if the normally if the B is 2HF here, this is isotropy, and we will call this is isotropy etching, and this is anisotropy etching. And we'll talk about edge selectivity, and edge selectivity is like this. We'll talk on example. This, can you see this picture? This is when unwanted area is etched like this here. We call it low edge selectivity. And if the edge selectivity high like this, and we only the target is etched. And we will talk about example of making FinFET. This is anisotropy etching. Can you see this? And this here we etch down here, and we can make this shape like this to removing mask. And finally we will make this. And in anisotropy etching, first this, and we regress here and here of using silicon, so we can make a bridge shape like this. And we'll talk about wet etching and dry etching. This is the method of etching, and wet etching is a method of removing the desired area by using a etchant. So it is cheap and simple, and we normally use isotropic process. And there is another way of etching, dry etching. Dry etching use plasma process or gas phase process, and we use normally this isotropic etching, and it is easy to control. And first we'll talk about wet etching, the process. First, the react is delivered to surface, and second, the chemical reactions occurs on the surface, and finally we removed byproduct. And wet etching is sensitive for temperature and concentration and chemicals, and the edge selectivity is high, and we will normally use isotropic etching and control. We can't control this easily, and the uniformity will decrease, but it is simple and cheap. And there is some etch principle in wet etching. Since ISIO2 etch, it uses HF, hydrogen polite HF, and there is a BOE. We use this to prevent from suddenly decreasing of hydrogen flight density. And if we use this, the edge light will we will make edge light uniformly. And we'll talk about the cutoff silicon lattice. And to put it simply, the diagonal is J111 plane, and the horizontal is 001, and the vertical like this is 110 and 011 plane, and this is 110 plane, and this is 111 plane, and there is some methods on silicon etching. There is isotopic etching. It uses hydrogen fluid and neutral SIN, and there is anisotropic etching, and it is there is we use aerospace etching. In aerospace etching, we use KOH, and in KOH, 011 etching is faster than 111, and 110 etching is faster than 111 or 500 times. So this means that 110 and 100 is similar, and there is a big difference with 111. And we'll talk about making FinFET. If we make FinFET on 100 substrate, and we use one here in diagonally 111 plane here, we can't make a fin shape like this because it is 111, so it does not etch well, and it goes down in a V shape, and then the bottom becomes flat like this. And we when we use 110 substrate, we edge works well in the downward directions like this, and but not well in the side directions because we use 111 plane. This is because this is in 110 plane. The 111 plane is horizontal line, so we cannot well in the side direction, so we can make this FinFET shape. So finally, since wet etching is difficult to do in nanoscale, so we have to solve the problems to etch together using methods such as placing barrier that I talked before. So this is the end of video. So thank you for watching.